example where we can use this knowledge from cylindrical coordinates first and then find the spherical. So if we want to use cylindrical, we can find theta using the cylindrical coordinate idea, and that is that tangent of theta is equal to y over x. You kind of remember this? It's familiar somewhat? Yeah? So what I know from here then is that tangent of theta equals 1, right? Which means tan inverse 1 equals theta, which is the same as asking where on the unit circle is tangent equal to 1, and there are actually two places. Pi over 4, and makes me nervous that we're thinking about it wrong, but I want you to think about it. What quadrant would I have to be in? Third form to match up, right? So I go pi over 4, 3 pi over 4, 5 pi over 4. Be the third one, the third fourth measurement I come to. I got to think about which one of these pieces of junk I want. And to do that, I come back over and I think about it in my graph. I've got that in the first quadrant, right? So which angle measurement am I going to choose? 4. Got my theta. Now I can find theta using cylindrical, and after that I can find rho pretty nicely as well. Because I know rho squared is equal to x squared plus y squared plus z squared, right? Which means rho squared is equal to 3. Do we think? Do we agree? I've got 0.111, right? So if I square all those and I add them all together, I get 3. Which means rho is equal to plus or minus root 3. I only need one of them though, right? And to make my life nice, I'm going to choose the possible. Question?
There's another way to find it. Find the process.
Rho?
Yeah.
This is rho.
So there's another way to find rho.
Oh, there's a whole bunch of different ways. This is just a set of steps. Yeah.
Right.
Theta, rho. Next one I need is B, right? Well, let's think here. I know that x is equal to rho cosine theta sine phi, right? Do you agree with that? I know that y is equal to rho sine theta sine phi, and I know that z is equal to rho cosine phi. Which one of these is going to be easiest for me to find phi? I can do z. In reality, any of them are about equally easy. I'm going to go ahead and use z. I know z is 1, right? Rho is 3 cosine phi, right? I'm going to go ahead and divide that off. I'll get 1 over root 3 equals cosine phi. Root 3 over 3 equals cosine phi. And why does this make my life not as nice as it could be? Not on the unit circle, right? Is that the end of the world, though? No, what am I going to do? I'm going to invert it, right? This is going to be cosine inverse. Root 3 over 3. Now, there's a little bit of a problem with this. What is it? What's the only problem I might run into when I do an inverse trig function? The domain is restricted, right? I had the restricted domain in the original one, which means the range, the output of the inverse trig function, does not cover the entire unit circle. I'm actually in luck though here. Cosine inverse. What is the range of cosine inverse? Anyone know? It's 0 to pi. So do I have to worry about this when I do cosine inverse? No, because what is phi restricted to? 0 and pi. Which is why I got so excited when you guys said z, because in reality, if we had done either of the other two, sine inverse is restricted between negative pi over 2 and pi over 2. We would have to worry about that one. Which means z, most convenient one to do here, whatever we get out here, will be our phi measurement. Coming over then, we've got root 3, what was it, pi over 4, and cosine inverse of root 3 over 3. If it bugs you, you're welcome to convert a decimal. If you convert the decimal, make sure, for the love of everything holy, that it is in radians. How do we feel about it, guys? Do we feel okay? Come on. Okay, so the big question then becomes, what are triple integrals going to look like? And it turns out they're not actually that bad, but the formula is going to look awful, just to warn you. So we converted, let's talk about integrating. Triple integrals in spherical coordinates. Okay, so what we're going to do is we're going to go ahead and define some three-dimensional solid E. This is what we're going to be integrating over. This is like that domain we've been talking about. So when we write it out, we're going to write it in spherical coordinates. So we'll have rho theta c. I've got to restrict rho. Rho is going to be restricted between A and B, just like I would restrict R, just like I would restrict the radius for cylindrical. Theta is going to be restricted between alpha and beta. And for some weird reason, sticking with the book here, we write C as restricted between C and D. Why did I say that was kind of weird? Why is that weird that that's the notation the book uses? What is C? It's an angle. What have we used C and D for in the past? Sides, and for what coordinate? Why, right? So it's kind of odd that we're reusing notation here, but I'm not one to argue with them. They know way more than I do. So what we're going to be talking about here is the triple integral over our solid E of f, x, y, z, dv. It's the same as splitting these up, looking at the iterated integral. I run rho from A to B, theta, alpha, theta. And let me make sure I'm lining this up with actually what the book does. I thought so. Guys, the Monday. Let's work backwards here. There we go. Much better. Much better. Why did I think that was wrong? Why did I notice as I wrote it down it was wrong? What should this line up with? The same type of idea we had when we did cylindrical, right? So I knew therefore that I should be going backwards with them. Okay, I write this as f, but I can't write an x in there, right? I'm going to write x as rho cosine theta sine phi. Rho, yeah, you did not leave enough room. You're about to find out. Sine phi. Z, which was really nice in cylindrical coordinates, kind of messy too, right? Rho cosine phi. Now, do you think that's all we have?
No.
No, why wouldn't it be? We need that extra thing on there, right? Now, it's not a straight over translation, and we don't actually have enough time to talk about exactly why. The difference is it becomes rho squared. Now, r wasn't equal to rho, though, right? R was equal to what? Rho. I'll let you look. I want you to look back. R was equal to rho sine phi. So a good way of thinking about this is I add in that R, and I added another rho, which means I can write it as rho squared sine phi. A little bit different than the direct translation over, and the reason behind this has a lot to do with the shape we're integrating over. The book, if you're curious, does Riemann sums for this. Riemann sums on a sphere. We do not have time nor the desire to do it. If you would like to look at it, you're welcome to. Now this being said, I need to write out my differentials. What differential comes first? Zero. C. Please make sure that your C's and okay, those look different. really useful when I had that circle imprint. That is when I was looking at integrating over a cylinder. Wonderful, integrating over a cylinder. What do you think this is going to be really useful for? When am I going to want to use it? When I have a sphere. Now that seems really obvious and kind of dumb. I mean, how often do you integrate over spheres? A lot. You integrate over spheres a lot because a lot of the shapes we're curious about in both physics or sciences have a spherical form. Even if it's not perfectly spherical, it's got the general shape. We'll do the approximations using it. Okay, this is nasty. The best way to conquer it is to go ahead and start by an example. So we're going to erase this. We're going to look at one. Of course, it would be really easy if I gave it to you in spherical coordinates. So I'm not going to. Okay. Example. Evaluate the triple integral over b of e to the x squared plus y squared plus z squared to the 3 halves dv, where b is equal to the set of all points x, y, and z, such that x squared plus y squared plus z squared is less than or equal to 1. Now, we said, and you guys understood, that it was going to be nice if we were integrating over a sphere. The big question is here, how do we recognize we're integrating over a sphere? To know we're converting to spherical coordinates, we need to recognize what the equation of a sphere is. What's the equation of a sphere? I'm good. Just like an x squared plus y squared plus z squared. And you should recognize this from your homework, right? Maybe equals some n squared equals some distance out in constant squared. So as soon as you see an x squared, a y squared, and a z squared, you should be thinking spherical coordinates. You see an x squared, a y squared, and a z squared anywhere? Yes! Twice. Okay. Sorry, I got okay the way there. Okay, so let's talk about b first. This thing. Okay. X squared plus y squared plus z squared. Spherical, right? What is going to be that outside radius of that sphere? 1. And I'm shading inside the sphere. How do I know I'm shading on the inside? Less than or equal to 1. The sphere that has radius 1 is really, really important in mathematics, especially higher mathematics. It's what we call a ball, hence the b, and it has a radius of 1. In 2 dimensions, we had something that had radius 1. It was circular. What was it called? So what do you think we call this? Unit ball, or unit sphere. Honestly, unit ball. Ball of radius 1. Very fancy shape. Okay, so what we want to do here is we want to set up our integral. So to set it up, first thing we're going to talk about are our bounds. If you cannot visualize the unit sphere, it's a good idea to draw it out. I can try. It's going to be pretty shaky, guys.
Oh, man.
Egg. Oh, man? You couldn't even like humor me here?
Sorry.
Okay, we'll make it a little better. There you go. It kind of looks like a ball now, right? Kind of. A little bit. Okay? Humor me here, guys. Humor me here. That's a beach ball. Okay. Okay, I've got a unit sphere. I'm shading on the inside of it. I like the face you're making. What I need to do is figure out what exactly my bounds are going to be, right? Now I have the entire unit sphere, so when I rotate around, what is theta going to be in between?